Okay, ladies and gentlemen, so today we are going to be talking about something called a slope field. Now, a slope field is going to look a lot like a derivative. It's not. It is a part of integration, mostly because we're going to be looking at something called differential equations down the road, and they're a big part of it. So basically, all a slope field is a graph of the slopes, all the possible slopes of an equation at a bunch of various points. So we're going to take a look at a very simple differential equation. We call this a differential equation because it's got dy dx in it. That's it. You've heard me use that term before, but that's basically all it is. So dy dx equals x. Sketch the slope field. So that's basically what the question is going to be looking like. This comes up on the AP Calc exam all the time. What they'll do is give you a slope field and ask you to draw in a curve, or they'll ask you what the curve fits. A bunch of different things that we're going to take a look at now. I've even seen an open-ended question where you actually had to sketch a slope field. So this is really important. So the very first thing you need is a graph paper. So I'll let you guys copy that down. We're only going very simple by 2's on the y-axis, 2's on the x-axis, and of course they're negative counterpoints. So you only need a very small window for this on your notebook. The reason we're doing it so small, again, is because it actually is a lot of little tiny things. I don't want to have to do a bunch of them. Okay? All right, so what I would like you to remember is that dy dx is actually the slope. Why? Because dy dx is derivative, and another word for derivative is slope. So if I'm asked to just sketch the slope field, all I need to do is substitute in the ordered pair. Let me show you a bit what that looks like. Okay, this is basically what we're going for here. Well, where in the world did they get this from? Well, take a look on this axis right here, and I'm going to switch to a highlighter. This might be a little easier for you guys to see then. Okay, all right, so take a look here. This right here, this is where the point x is 0. And y is 3. Okay. Well, if x is 0, I'm just plugging it in right here. If x is 0, notice there's no y here, so it doesn't matter. So if x is 0, the equation itself is 0. And if the equation itself is 0, that means it has a 0 slope. Well, I don't know why the highlighter's not working with me today. Still not working. Okay, so 0 slope, 0 slope, 0 slope, 0 slope. Now, here, this is all positive 1. If I plug positive 1 in for x, I have a positive 1 slope. So there's my positive 1 slopes, positive 1 slopes, positive 1 slopes. Okay, and that's all the way down because, again, there's no x value that is interfering here. 2, positive 2 slope right there. Okay, 3, positive 3 slope. Over here, it's a negative 1 slope, negative 2 slope, and negative 3 slope. Okay, so again, all you're doing is you're taking the point itself and you're plugging it in to this equation. Okay, I'm going to get rid of all that highlighting, and that way you guys can add it to your notes. If you want, actually, let me go back to the previous slide and I can show it to you a little bit slower. I just wanted to kind of give you the concept. There we go, and back. All right, so we're looking at it a very small. So at 0, this point right here, x value is 0. So I'm going to plug 0 into this, and I get 0. A line with a 0 slope is horizontal. Here, the x value is still 0. I plug in 0, I get 0. Here, same thing. Here, same thing. And here, same thing. Okay, now let's go to these points. This is x is 1. If I plug 1 in here, I get 1. A positive 1 looks about like that. This is still 1. Again, the y value is changing, but there is no y over here in the equation. So everywhere x is 1 is a positive 1 slope. Here is 2. Anywhere that it's 2 is a positive 2 slope, so it's a little bit sharper. Okay. Again, you don't need to be perfect when you're doing this. Just keep in mind 2 is sharper than 1. Over here, it's negative 1. If I plug in negative 1, it stays negative 1. So let's put our negative 1s in. look even, but I'm not the artistic one. And so finally, -2, those are much, much sharper. Now, what your slope field is going to start revealing to you is the curve that would come if you were to integrate this. Does everybody kind of see it looks like almost like a parabola? Well, if I was to integrate x, I would get x squared over 2, correct? Well, that's what this slope field is actually showing that we have here. So again, all the slope field's doing is finding out, well, what's the slope at all these little points? And then if I connect those points, I should be able to come up with the original function that has that slope. Okay, so that's basically all we're talking about. I'll leave it there. Again, it's not anything more involved than that. That's basically what our lesson is today. All right, so now I'm moving on. Okay, so this again, it's a bigger slope field, but that's okay. We can do it. You can use your notes with your smaller slope field. This says sketch the curve 0, 1. Okay, graph the point given. Well, we're going to go to 0, 1. That's right here. We're going to graph the point. And then you want to kind of smoothly flow from dash to dash. In other words, what looks like the closest point from here. Okay. It helps to know what it looks like. We did that on the previous slide. 1/2, that is when you're kind of smushing down your function. It looks like it's kind of getting sat on. So it looks like, since this is a horizontal line, it's coming out a little bit, which is kind of drawing us to here. Okay. And then this one's kind of allowing us to tilt up a little bit to here, which looks like it's coming up to here. On the other side, again, it was a flat line, so I'm extending that until I hit the next hash mark, which is letting us curve up a little bit. Okay. All right, there we go to this hash mark. And then up to this hash. But that looks a little bit sloppy, but I'm working on a stylus. Okay, so that's basically all you're doing, and that is a particular function through this particular point. Anytime you're asked to give a particular function, you're just trying to find the hash marks that look like they see the most. All right, so example 2, let's sketch the slope field this time of dy dx equals y. And the curve, if 0, 1, is on y equals f of x. I'm going to wait for a second so you guys can copy this down. Okay, so the most important thing of this, again, is to go point by point. We're using a very small axis. That way we're not drawing lots and lots of points. So I like to start always at the origin. Now, notice in this equation, the only thing you're caring about is the y value. So right here in the origin, what's my y value? Y value is 0. Well, a slope of 0 is, once again, a horizontal line. Okay, now if I come up here, my y value this time is 1. Well, 1 looks kind of like that. Here my y is 2, and so that's a little bit steeper. Okay. Down here it's -1, and here my y value is -2. Now, this point my y value is still 0. This point my y value is still 1. This point my y value is still +2. Okay. This point my y value is 0, 1, and +2. This y value is -1 and -2. -1, whoops, sorry, that looks a little flat. -1 and -2. Okay. So, okay, up here, this is still a +2, a +1, a 0, a -1, and a -2. And here it is a +2, Sorry about that. A positive 1, a 0, a negative 1, and a negative 2. So there is our slope field. Notice how it looks kind of like it's almost a square root function. This is basically the inverse of what we were previously working on. All right, so the curve is at 0, 1, so that point's right here. Now notice how it was curving upward. Looks like it's going to run right into that point right there. Okay, coming this way, it looks like it was coming down. So I would say it looks like it's going right through there. And there you go. And again, it looks like that from last year, that square root. The reason is because if I were to integrate this, it would be y squared over 2, which, as you guys know, if I was solving for x, would be the square root. It is a square root function. It's there to labor by. Okay. All right. Hopefully so far there's no questions on these. Please email me if there are, either through NGrade or through my actual email, which is mkolb@patterson.k12.nj.us. Okay, moving along. So question, why are there so many dashed lines? Quite often when I'm teaching this, and so I'm kind of expecting you guys are thinking it too. The reason is because you have this unknown constant, that c. That c could put it anywhere. So we have to account for it to be anywhere. The nice thing is it can show you the entire family of a graph. In other words, it can show you a quadratic placed everywhere. It's not a specific quadratic. Or a rational function placed everywhere, or a sine function, a sine curve placed everywhere. So the whole family of sine curves. Okay, but that's basically what slope field kind of stands for. All right, so does the following slope field have a horizontal asymptote? If so, where? Well, horizontal asymptote is once again a horizontal line. So what I'm doing is I'm looking through here and saying, do I see any horizontal lines? And the answer is yes, actually I do. And that's through -3, right down here. Okay. -3. Next one. Does the following slope field have a vertical asymptote? If so, where? Well, vertical lines going up and down. So I'm looking to see, does it look like there's a line here that looks like it's going up and down? And it's actually right here. That looks like x equals 2. If -1, 0 is on y equals f of x, which of these other points could be on y? Well, that means we need to graph it. -1, 0 is right here, and that looks like it was tilting upward to here, which looks like it's also tilting upward to here, and then it hits an asymptote, and you guys know asymptote means it's going to hug the asymptote, but it's not going to cross it. Now let's come down the other way. It looks like it was tilting to this one. Okay, which looks kind of like it was coming down to this one, to be honest with you, from there. I mean, you guys might see it a little differently. And then it looks like it's bottoming out from there. So there we go. So -4, 1. -1, nope. 1, 3. 3. Oh, there it is, 1, 3. Okay, that point is in fact on the curve. 1, nope, that would be 1, 2. Sorry about that. -8, 4, and -1. Yeah, I think I would go with 1, 3 on this one. That one looks like it's closer to where it could have been if I had maybe chosen to come up to this problem instead. And again, it's one of those approximations, which of these other points, I think you could actually argue for -1, 1. No, you couldn't. And -4, 1 doesn't make any sense. It doesn't look like it's coming anywhere near that one. Okay. All right, moving on. Family of graphs. Well, you guys should know what this one looks like. It looks kind of like our check marks. It looks kind of like our butterfly, our rational graphs, back when we were curve sketching. Okay, and again, so the curves could be here, 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 but importantly, it's noticing that shape. concavity at 4, 2. Well, let's find the point 4, 2. Positive 4, 2. All right. Everybody notice it kind of looks, let's see if I extend some of these little lines right here. That looks like it's definitely concave up. Everybody agree with that one? Definitely looks like it's up. Okay, cupping upward. So that is a positive concavity. Now, sketch fields for the following differential equation using lattice points on negative 3, 3 by negative 3, 3. Okay, so once again, this is y prime. That is once again a slope. And it looks like we're looking at 2 minus x. So again, y value doesn't matter. So I like to start at my origin. My x value here is 0. So 2 minus 0 is 2, which means we have a positive 2 slope. The x value stays the same all the way up. So I'm just going to go through and put all of my hash marks in right away. 1. 2 minus 1 is 1, so I'm going to put that hash mark in. Okay, 2 minus 2 is 0. That's a horizontal line. And then 2 minus 3 is negative 1. And again, I'm going all the way down because there's no y values involved, so I know it's the same subtraction each time. All right, over here, 2 minus negative 1 is positive 3. Oops. Yeah, so positive 3. Positive 4. Whoops, that didn't look like positive 4. And again, you got to just kind of approximate this. It's a sketch. It's not based on accuracy. Okay. This one is negative 3, so 2 minus negative 3 is positive 5. That's almost going to look straight up and down at that point. And again, these are all the same back here. Okay. Looks like it's coming down there, and it looks like it's also coming right down through curve. Again, if you had integrated this, you'd have noticed it's 2x minus x squared over 2. So it should be a negative upside down parabola. Mine looks a little demented, but you know, the better. So first and foremost, I like to start at the origin, like always. 0 minus 0 is 0. Now, this is the point where x is 0. Okay, x is 0, y is 1. 0 minus here, x is 1, y is 2. That's negative 1 slope. And then x is 1, y is 3. That's a negative 2 slope. This point, x is 2, y is 0. That's a positive 2 slope. This is x is 2, y is 1. That's a positive 1 slope. 2 minus 2 is 0. And then 3 minus, okay, so 3 minus 3, I'm starting back here, is 3. 3 minus 0 is 3. 3 minus 1 is 2. 3 minus 2 is 1. And then, of course, 0. Down here, 1 minus 1 is positive 2. 3 minus 1 is positive. 2 minus 1 is negative 2, negative 3, negative 4, negative 5, and finally negative 6. So there we go. We have a point through 0, 1. Okay, that's like this. Looks like okay, maybe that. Okay, this is kind of like a hyperbola, so it's actually got a matching sequence down here as well. It's kind of like a rational function but tilted a little bit. Okay, all right.